Hello, everyone, and welcome to the DI 101 webinar series. This series, if you are new to this series, I'll tell you that it is an incredible resource offered to our customers, partners, and associates. By partnering with our manufacturers and our industry experts, we deliver informative presentations about industry trends, new technology, new products, and product applications. We're extremely excited to partner with Owens Corning FOAMGLAS for today's webinar. Today's webinar will discuss cellular glass insulation systems for corrosion under insulation mitigation. The presence of moisture is necessary, as we all know, for CUI to occur. Obviously, two ways that can help mitigate CUI are: one, keep water out of the system, or two, give water away out of the system. This webinar will describe the risk factors of CUI and two different FOAMGLAS cellular glass insulation systems designed to help address the control of moisture: the FOAMGLAS Sealed System and the FOAMGLAS Spacer System. Let me introduce our presenter. From Owens Corning, we welcome Alec Cusick. He is the Technical Services Engineer for the Industrial FOAMGLAS business at Owens Corning. Prior to his current role, he was in technical sales for fiberglass and mineral wool mechanical insulation at Owens Corning. He holds a Bachelor of Science in Mechanical Engineering with a minor in Professional Sales from the University of Toledo. We are proud to have Owens Corning FOAMGLAS present today, and we certainly thank them for their time. We will pause for questions at the end of the webinar. To submit questions, please use the Questions tab on the GoToWebinar control panel. You can submit your questions at any point during the webinar, and we will answer those questions during that questions period at the end. So if we won't do the unmuting or raising hands, so we'll only use that questions tab. So please keep that in mind. Without further delay, I will now turn this over to Alec Cusick with Owens Corning FOAMGLAS. Alec?
All right, thank you very much, Jared. I want to start off by thanking you once again for the opportunity to be a part of this ongoing procedure of getting involved with continuous education for the industry. We're excited to be a part of it. Looking forward to today as well to discuss around these systems, around the mitigation of corrosion under insulation, as has just been mentioned. So without further ado, I will go ahead and get started. I'm going to introduce today's panelists that will be joining me around this topic. Joining me today, I have Alan Dickey, a Senior Product Manager for Systems and Specifications for Industrial FOAMGLAS. He's been with FOAMGLAS for 32 years and is a primary contact for our FOAMGLAS guide specifications. Tim Bavard is our Manager for Technical Services and Training for Industrial FOAMGLAS. He's been with FOAMGLAS for 40 years, and he leads our technical services and training programs for the Americas and Asia Pacific. Luke Schmout is our technical product leader. He's been with FOAMGLAS for over 10 years, and he leads technical services for Europe, the Middle East, and Africa. And he's been involved in the development and commercialization of our spacer system within the North Sea area. Brandon Stambaugh is the Director for Product Management, Technical Services, and Training. He's been with FOAMGLAS for 24 years, and he leads our Product Management and Technical Programs Department for Industrial FOAMGLAS. Bill Rose is a Sales Director for the South region of North America. He's been with FOAMGLAS for over 25 years. He's a sales leader for North American Industrial FOAMGLAS and is primarily accountable for the South region of the United States. Bobby Farrell is our Industrial Applications Engineer. He has over 40 years experience within the industry, and he handles our application training programs for Industrial FOAMGLAS. And then Doug Fast is our technical leader joining us as well. He has over 20 years experience within the industry and is a senior engineering lead for us with industrial fiberglass and mineral wool. So before we get started into the bulk of the presentation, I'd like to take a brief minute just to introduce Owens Corning for anyone not familiar. We are a global leader in engineered materials for insulation, roofing, and composites materials based out of Toledo, Ohio. Our insulation business is built around leveraging our global platform to deliver quality products and innovative solutions that are safe, durable, efficient, and high performing over a wide range of service temperatures. Our product portfolio includes open and closed cell insulation solutions, including FOAMGLAS Cellular Glass, fiberglass, Paroc and thermofiber mineral wool, and FOAMULAR extruded polystyrene. And being a global insulation business, we have over 7,400 employees across 20 different countries, and we also have 43 different manufacturing locations that allow us to service jobs across many different markets. So here you can see a brief agenda of what we will be covering today. We're going to start with the basics of what is corrosion under insulation, or CUI. Then we'll talk about the main risk factors that contribute to CUI. Next, we'll cover common industry strategies currently being used to mitigate CUI, followed by what criteria to look for when selecting your insulation system. And finally, we'll cover 2 new systems from FOAMGLAS specifically designed for mitigating CUI. So I'd like to start off with just a initial question to ask the audience: what is corrosion under insulation? We're just going to dive into this topic right now. So I'll start off by simply defining what corrosion is. NACE, which refers to the National Association of Corrosion Engineers, defines corrosion as a naturally occurring phenomenon commonly defined as the deterioration of a material, usually a metal, that results from a chemical or electrochemical reaction with its environment. I know it's a mouthful. Simply put, it's the degradation of a material into a more chemically stable version of itself given its environment. In a 2016 report, NACE estimated the global cost of corrosion to amount to $2.5 trillion, which for comparison equated to roughly 3.4% of the global GDP at the time of the study. So you can get just a bit of an idea as to how large a scale of a problem that corrosion is on a global basis. NACE then goes on to define corrosion under insulation, or CUI, as a severe form of localized external corrosion that most commonly occurs on insulated carbon and low alloy steel and stainless steel equipment. Carbon steel and stainless steel corrode via different mechanisms, but in today's presentation, we'll primarily be focusing on the corrosion of carbon steel pipes. And you can see listed here just a brief list of some potential consequences of corrosion under insulation. It can lead to unanticipated failure of the process system, damage to expensive equipment, costly repairs and or downtime. And if it gets serious enough, or if it's on a significant process, it could be a safety hazard. It could lead to failures that result in fires or explosions, or worst case scenario, you'd have to avoid it, but injury or death are something you want to be thinking of and keeping in mind when you want to mitigate CUI. So there are 3 primary risk factors that contribute to the increased risk of corrosion under insulation. They are the presence of moisture, the chemical content within said moisture, and the presence of heat. We'll now try to understand the role that each of these factors plays in corrosion. So we're going to start off with moisture, the first one we just listed on the previous slide. It is often well understood that wet insulation can lead to various process and efficiency losses within a system, but the presence of liquid moisture or water also happens to be a basic requirement for corrosion to occur. There are numerous potential sources for water to get into an insulation system, such as condensation, normal precipitation, process leaks, or even mechanical intrusion from sprinklers or cleaning processes. Those last couple on the list, I'd like to hit home a little bit. Sometimes it goes overlooked, but if you're working on a facility where part of the planned maintenance for a given system will be the occasional hose down of the equipment, you'll want to keep that in mind, as that presents a big risk for water to penetrate the system at some point during the life of said process. So once moisture is available within the system, the chemical content of said moisture can dictate the rate of corrosion that occurs. Starting off on the left, generally speaking, the more acidic on the pH scale a given solution is, the more aggressive corrosion it will yield on steel surfaces. Additionally, taking a look on the right, the presence of chloride ions or other contaminants that increase the electrical conductivity of water can also accelerate corrosion. Chloride ions can be introduced into a solution when molecules like sodium chloride, or salt as it's commonly known, are allowed to dissolve in water. This can come as a result of pollution from the external environment or by leaching from components of the insulation system that the water comes into contact with. Another thing to hit on is that the presence of heat is one more factor that contributes to accelerated corrosion. As long as liquid moisture is available, the corrosion rate will increase with temperature. That means that the primary surface temperatures that are at risk of corrosion are somewhere between roughly 25 and 350 degrees Fahrenheit, where it's feasible for liquid water to penetrate a system and still be able to come in contact with the steel pipe. On the cold end of this spectrum, corrosion may still be taking place, though at a slower rate than at higher temperatures. Whereas on the hot end, corrosion occurs much more rapidly. However, as you start to approach temperatures above roughly 300 degrees Fahrenheit, it becomes less and less likely that liquid moisture will be in contact with a pipe, as it may boil off as vapor before coming to rest against it. For pipes that operate below ambient temperatures, there is a constant vapor drive from the warmer environment to the cold pipe surface. For permeable insulations or insulations that are not properly installed, this vapor can quickly move into the system where it then condensates on the pipe or within the insulation itself. On especially cold systems, this condensation may turn into ice, which, being that it's not liquid, does not inherently contribute to corrosion. However, if the system is allowed to then warm up as a result of the system shutdown or cycling processes, that ice can then melt and introduce a large amount of liquid water onto the steel pipe, quickly becoming an environment for corrosion to take place. Similarly, we can take a look at what happens to permeable or poorly installed insulations on hot pipes that operate above 350 degrees Fahrenheit or so. If moisture is allowed to penetrate the system, liquid water near the surface of the hot pipe will boil off as vapor. This can, in a sense, force any liquid water present away from the pipe, where it often settles within the insulation itself at some thickness. Here, the liquid that can become acidic or concentrated with chloride ions over time as it leaches from components of the insulation. Then, if the system is allowed to cool off during a system shutdown, this now chemically harsh solution can freely move to the surface of the pipe, where it settles and can cause rapid corrosion to take place. Now we're going to talk a little bit about what strategies are commonly used already around combating these risk factors we've just talked about. One of the most common methods of mitigating CUI is the use of a vapor retarder to prevent moisture from penetrating an insulation system. These are seen all over the place. They can be effective when used over rigid insulation materials. However, they are susceptible to physical damage and can fail entirely if not properly installed. Paints, mastics, gels, or other coatings can also be used as a physical barrier between the pipe and the insulation itself. Foils are also sometimes used as a physical barrier for cathodic protection, where they're installed directly over the pipe and underneath the insulation. In general, most approaches of mitigating CUI will come down to one of three methodologies, and that is to A, keep water out of the system, B, to give water away out of the system, or C, to allow water in but change its chemistry as you do so. Now we're going to discuss some things to keep in mind when considering what you would want to use as your insulation system when mitigating CUI. While today we will be focusing on the insulation system, I'd like to take a minute just to point out that the insulation materials alone are not a solution for CUI, but rather they should be used as a component of an overall strategy that takes multiple areas into consideration. When designing a system, one will want to give thought as to what pipe materials would be best for your process, what your insulation components should consist of, what claddings, coatings, or other tertiary materials you should use alongside them, and what your inspection and maintenance plan will consist of. Designing with all of these criteria in mind is crucial for developing an effective and long-lasting system. Now, when selecting an insulation system for the mitigation of CUI, there are multiple questions one should ask themselves. Does the material perform in the process temperature range? Does the material wick, absorb, or retain moisture? Does the material retain its dimensional stability? Does the material have chemistry that causes moisture pH to become acidic? And does the material contain chlorides that could leach into water if it comes into contact with it? So when considering these issues we just established, there are many characteristics of foam glass, cellular glass insulation that can help mitigate CUI. Starting off, cellular glass insulation is the only insulation material that's truly impermeable. As being composed of glass walls, it will not wick, absorb, or retain moisture. It's also dimensionally stable, having a coefficient of thermal expansion similar to that of steel. It's chemically inert and does not promote the corrosion of carbon steel or stress corrosion of stainless steel. It contains a low amount of leachable chloride ions and has been tested for compliance to ASTM C795, specifically for use on austenitic stainless steel. Foam glass is easily fabricated into a multitude of shapes and configurations, and we currently offer an extensive portfolio of compatible accessories specifically engineered to form complete insulation systems. From here, we're going to introduce two new systems from FOAMGLAS, specifically tailored for CUI mitigation. They are our FOAMGLAS Sealed System with our proprietary joint sealant technology, and our FOAMGLAS Spacer System with proprietary spacer technology. So we'll start off talking about our FOAMGLAS Sealed System, which, as discussed earlier, follows the methodology of keeping water out of a system. So the FOAMGLAS Sealed System utilizes the natural impermeability of cellular glass insulation to its advantage. It's applied in a way to seal all joints and compartmentalize insulation system components from each other. Some additional benefits are that it requires no additional additives, and it uses traditional sealed cold system techniques that many installers are already familiar with today. A key component to the FOAMGLAS Sealed System is our proprietary Pit Seal high temp LV RTV sealant. This sealant is specially formulated to be a low viscosity, which enables it to efficiently spread and seal all joints within the system. It neutral cures to an elastomeric solid at room temperature, does not contribute to corrosion, and boasts a wide service temperature range from -238 to positive 450 degrees Fahrenheit. It is important when installing this system to ensure that full depth of coverage is achieved with all sealant at all joints, terminations, and protrusions. In this example, you not only have a full thickness of sealant at the joints at this protrusion, but due to its impermeable nature, the full thickness of foam glass insulation acts as its own seal to the system as well. Here you can see some photos of the sealant being applied to a protrusion in this manner. Notice how enough sealant is applied to ensure that it spreads evenly across the entire mating surfaces of the insulation when the two pieces are pressed together. So where would you want to specify this new FOAMGLAS sealed system? Well, we recommend using this where CUI is a concern and on below ambient piping with a high vapor drive towards the cold pipe, on underground or direct buried applications, on above ambient applications or applications that are cyclical in nature, or areas where other conditions are present that require the use of a sealed system. Notes that it is not intended where continuous immersion is expected. We at Owens Corning offer a wide array of documentation and support for the sealed system that goes anywhere from application guide specifications to product data sheets, safe use instruction sheets, detailed drawings, technical supports. We can handle any technical questions you may have that come in. We have application test reports, and we even have application training opportunities to help instruct your team how to properly install it in the field. During development, we also conducted multiple different tests to document the performance of this system. One of these was a modified ASTM test that tested the system within 2 different controlled environments over 28 days. One chamber was simulated with a salt solution of rain, while the other was simulated with a salt solution of rain and fog. In our experience of running these tests, they are considerably harsh to unprotected metal pipes and often exhibit very obvious signs of corrosion upon conclusion. Here on the left, you can see an example of what a typical unprotected pipe will look like upon conclusion of this 28-day test. You can see, just based on the surface alone, very obvious signs of heavy corrosion taking place. Where on the right, you can see the 28-day results of the FOAMGLAS Sealed System for both rain only and rain plus fog. Note that the faint orange color that you may be seeing in the middle of that system is actually from the sealant during the installation of the system and not indicative of corrosion taking place. So now we will move on to discuss our other system, which is our FOAMGLAS Spacer System, which follows the approach of giving water a way out of the system. Excuse me. Our FOAMGLAS Spacer System is a prefabricated solution consisting of traditional foam glass insulation suspended around the pipe with specially designed spacers. The air gap that's generated allows for liquid moisture within the system to collect away from the surface of the pipe. Small drain holes are then cut into the bottom of the insulation to allow for the water to leave the system via gravity. Additional accessories are used to compartmentalize the system, creating multiple predetermined sections that each allow for drainage to occur. The air gap that's generated from the system is actually ideal for supporting heat tracing configurations, and it's even been tested to meet Class A and B acoustic requirements of ISO 15665. Moving on to some of the accessories of this system, the system utilizes proprietary silicone spacers and termination strips, as you can see on the bottom right, to effectively space the foam glass off of the pipe surface. These components are adhered to the insulation itself using our PC high temp RTV adhesive. We then utilize the same pit seal high temp LV RTV sealant found in the sealed system to seal the joints between insulation sections. The termination strips and impermeable cellular glass insulation allow the system to be compartmentalized every few feet, where drain holes are then introduced to allow any water present to quickly leave the system. So where would you want to specify this new spacer system? Well, we recommend it where CUI is a concern and where water intrusion is probable from secondary sources, where you're using it on above ambient and hot systems with continuous or near continuous operation, on systems where acoustical consideration is needed, often used on offshore marine applications. And as we mentioned earlier, it's very good at supporting heat tracing configurations given the air gap that's present. Note that it's not intended for below ambient or hot cold cyclical systems, direct buried systems, or again, systems where continuous immersion is expected. Here you can see a list of current reference projects where the system has been used. As you can see just by taking a quick look here, it is often favored for offshore and marine type applications. So just like the sealed system, FOAMGLAS offers a multitude of documents and support for this spacer system. We have application guide specs around fabrication, product data sheets, safe use instruction sheets, detailed drawings, field references. Once again, application training opportunities to ensure that your team knows how to properly install it. We have a technical bulletin on the thermal effect of the air gap that's introduced into this system, as well as acoustic test reports on the acoustic performance to ISO 15665 that we mentioned earlier. One thing I'd like to reinforce right now is that we have a whole dedicated guide specification specifically around the proper fabrication of this spacer system for being sent into the field. This guide specification will allow this system to be fabricated to consistent and correct dimensions for various pipe sizes so that segments can show up to the job site properly sized and ready for installation. So in summary, CUI can have very severe consequences on your system. You want to understand the risk factors for your specific process when trying to mitigate CUI. CUI can be controlled with a comprehensive strategy, which includes the proper selection of installation systems. Our new FOAMGLAS Sealed System and FOAMGLAS Spacer Systems may be included as a part of this strategy that you may use for mitigation of CUI. As a final point of emphasis, proper installation is imperative for any of the systems that we've mentioned here today. One should always ensure that application guide specifications are being followed, proper materials are being used, and all installers are properly trained. Our technical team at FOAMGLAS frequently hosts in-person training sessions at our facility in Fresno, Texas. Please reach out to us if you have any interest at all in scheduling one for yourself. We'd be happy to work with you. Additional information about these systems can be found at our website, foamglass.com. We also have articles that have been published on some of these systems and methodologies discussed here today, both from materialsperformance.com and Hydrocarbon Engineering. Feel free to contact us for a copy of either of these articles. And with that, I'd like to once again thank you all for joining here today. We were very excited to be a part of this ongoing program with DI. Thank you again, Jared, for reaching out and getting us involved. And with that, I believe we'll be opening up for some Q&A.
Thanks, Alec. Really well done. It was really informative. Thank you so much for doing this. I don't have any questions in yet, but I will stall just a little bit to give people time to get some questions rolled in. So what I will do is remind everybody to go follow Distribution International on LinkedIn. We always post our upcoming webinar announcements on LinkedIn, along with so many other great information and announcements. So be sure to follow us on LinkedIn. Also, go check out, we have a YouTube channel as well. And we always record these webinars and post them on our YouTube channel. So if you go to YouTube and you search Distribution International, you should see a fantastic library of past webinars from this series and other great videos as well. So either I didn't stall long enough, or you already answered everybody's questions, because I don't see any in here yet. Is there anything anybody from the panel would just like to add? Okay, it looks like we have one question come in. I sent that to the panel, so I'll let you guys answer that as you see fit.
So the question is how tall is the spacer? Luke, you want to take that, or I can take it? Doesn't matter.
Okay, Bill, I will take it. The spacer, the air gap is 1/2 inch, 12 millimeter, and that's let's say the standard air gap, 12 millimeters.
Great, thanks. Let's see, no other questions. Okay. Oh, here's one. I'm just going to read this out and let you guys answer, if you don't mind. Is the spacer system then fabricated to still fit common OD?
Yeah,
it's more
so
of a
fabrication is made upon the, let's say, the OD of the pipe, so it will fit any diameter. So there is no exclusion on diameter or sizes or dimensions, so it is fit to the pipe. Yeah.
Okay. Another question: do you have a recommended drain system?
We have two systems. Some customers drill holes in the foam glass, 15 millimeter diameter. Others drill holes 17 millimeter and put a drain plug in, which then also has 50 millimeter free space. So either of the two can be done. North Sea regions, normally they drill holes of 17 mil and put a classical drain plug.
Alrighty. Last question we have, why is the spacer system used offshore versus a sealed system?
Alan, you want to take that one?
Basically, it's a lot to do with the ability of them to get to be confident that they're sealing the system completely on an offshore platform, and therefore it seems like there's a preference to use both systems. Are great and will do the job. However, it seems that in those cases there seems to be a preference in the offshore platforms for the spacer system.
Yeah, I would also add to that offshore there's a lot of electrical heat tracing that's done as well. And so these systems are also very, electrical heat tracing can happen very easily with the spacer system. So. And
also we have to add the temperature, the surface temperature, of course. The spacer system is between ambient and 200 C. If you have temperatures below ambient, then the sealed system is preferred.
Okay. I have another question. When you use the spacer system, would the OD of the insulation then be different where jacketing and metal fittings may not fit?
Luke, you want to jump in on that one?
Well, no, there is no, let's say, exclusion. So we make, okay, in Europe we fabricate the pipe sections on demand. So it will be fitting to every fitting and pipe, whatever diameter or whatever wall thickness. So it can be easily done. And there are no standard EID dimensions for foam glass. So meaning that every section we make, a pipe section or fittings, will always be made upon the dimensions that are required. So there is no, let's say, issue on dimensions or things that won't fit. It will always be made upon drawings or upon demand from the customer.
If I could add there, if you're fabricating, and this is something where we work with our fabricators, where if they're fabricating to ASTM 585, the ODs would all be the same. It's just a matter of the amount that's cut on the inside, but as far as the actual thickness to achieve the proper nesting sizes of diameters would still be obtained.
Yeah. So the idea of the FOAMGLAS is always 1 inch more than the pipe OD. So that's we have the dimensions. Standard dimensions are not a problem, and even if it's non-standard, there shouldn't be a problem to fabricate fitting insulation to that.
Okay, last question. Would not the spacer system work better for expansion and contradiction?
I think that's probably contraction.
Right. Yeah, I'm sorry. Yeah, there might be a typo there.
I'm going to get Luke. You can. It's back to the spacer system. You're our spacer system specialist. So why don't you?
Okay. Yeah, due to the fact of the design, of course, you have the silicon spacers in between pipe and insulation that will absorb vibrations, but also movement, expansion, contraction of pipe. So this is, let's say, the performing very well acoustically, but also for contraction, expansion, absorption. So there are some advantages for the spacer system, but you have to consider that it's designed for temperatures above ambient, and that should stay above ambient. Otherwise, the design is so that it is not, let's say, appropriate for below ambient temperatures. But for the rest, there are, let's say, a lot of advantages, especially on the fact that it's there is a space between insulation and pipe, which is vibration and movement absorbing. So there are, let's say, less stresses on the insulation.
Great. I think that was the last one. Thank you so much to Alec and the entire panel. Everyone at Owens Corning FOAMGLAS, thank you so much for your time, and thank you for your active continued participation in this webinar series. We really believe it's a good thing, not only for our associates and our customers at DI, but just for the industry in general. And we appreciate you guys doing this. With that, I just want to remind everybody to stay safe, and we will keep you posted on upcoming webinars. Follow us on LinkedIn, or go to distributioninternational.com to see what webinar is coming next. Thank you, guys. Have a wonderful day.
Yeah. Thanks, Jared.
Thanks.
Thank you.
Thank you all.